Whenever machines do work, whenever objects move, energy is being used. And energy comes in many forms, not to be confused with energy sources. The forms of energy, examples are electricity, heat, light, sound, motion of objects, chemical energy. These are forms of energy, and they can be converted from one to another. Let's ponder this question a moment. We eat food. We take energy from the food we eat, chemical energy, and we convert some of it to heat and some of it to motion whenever we move. Let's take the motion of our hand pushing a door shut. That energy that we consumed is now being used into the form of motion. That motion that's pushing the door shut is not only closing the door, but it's creating a certain amount of heat. Heat along the carpet, heat along the door when it hits, and heat in the hinges, and maybe even some sound. So we have energy conversion going on constantly. There's devices that convert energy, energy conversion devices, and they're all around us. And this is a good topic to get your class involved in a discussion when they're talking about energy forms. Have them name some energy conversion devices. Sounds like a big word, but they're simple things, things that we use every day. Like a match converts chemical energy into heat and light. Like a toaster converts electrical energy into mostly heat and some light. And like batteries, electricity is one of my favorite because batteries convert chemical energy to electrical energy, and we can then take that electrical energy and convert it into many other forms very easily. We can get heat and light from it, we can get motion from it, from an electric motor, we can even get sound from it. And every time that energy is transformed, say from one pile to another, there's always some lost. And it doesn't really leave the system, it just doesn't end out on the second pile. It goes off into a different direction, usually in the form of heat. Some energy transformation devices are very efficient. This means that the energy that we start with almost all gets transformed to the new form. Some energy devices are not very efficient at all, and that means that much of it goes off into some other direction and gets lost, and we can't use that new energy. We need energy to do work. Work, although most students see as defined in a different way in a social term, we see work in science as exerting a force through a distance. An object must move for work to be performed. Now, here we have an activity where we can actually demonstrate and measure the amount of work. Let me show you what I mean. We're using a piece of wood as an inclined plane, and on the piece of wood we have a 2x4 with a little eye bolt in the end and two rubber bands that are tied together. Next to the rubber bands we have a piece of cardboard that has numbers marked off, and I just use 1 centimeter increments, and these are just pinned on. What we want to find out is how much work is required to pull this block from here up to here. And remember, the way to find that out is work is force times distance. So we stretch the rubber band and we see where the knot is, and the knot looks like it's right on the 9. So it takes 9 units of force, and we need to measure the distance. Say it was 50. So 9 times 50 is 450 units of work required to get this block from here to here using this inclined plane. Now let's take a look at the other question. What about the fellow that says, hey, I don't want to use the inclined plane, I just want to lift it up from here to here? The distance is much shorter. We're going directly up, and the distance in this case is 8 centimeters. What is the force? Well, since we're going directly against gravity, we just hang it and we find that the force is 11. The knot and the 11 line up. So we have 11 times 8, 88 units of work required to do this. And the first question your students are going to say is, why would I want to use an inclined plane when I exert 88 units of force just by lifting it up, and it takes 450 to drag it up that ramp? Well, the value of a machine, once again, is the mechanical advantage. Say you're not strong enough to lift 11, but you can lift 9 or 10 even. So you can see that you can actually get the work done, whereas you wouldn't be able to do it in the other case. There's many activities that you can do with this little inclined plane, and it doesn't take much to put these together. You can have 8 of these in little groups working on their own, following an instruction sheet, and investigating simple machines and friction. We can go on one step further. Get a piece of sandpaper, tape it on or tack it on to the wood block, and let your students then calculate the amount of work required to get that block up to the top. They start to see that the energy they're putting into the system isn't all being used to move the wood block. And this is energy transformations again. Much of it is being lost, and in this case it's being lost in friction. Don't stop here, because there's a creative extension to this activity. Challenge your students to devise a way to reduce the friction and thereby increase the efficiency of the machine, where more of their energy goes into moving the block and not being converted into heat. What can they do? And if you need to give them a hint, you can talk about rolling friction versus sliding friction, and you can show them a coffee can like this. We have inside the lid a bunch of marbles, and the coffee can spins on the marbles, rolling friction, and it's very easy to turn the coffee can. The students will go on, make their guesses as to how they can reduce the friction on the sliding block of wood. Go on and test them. This is what science is all about. See how useful their ideas are. While you're on the subject of work, ask your students, what are the units of work? What are we measuring? What's the words that's supposed to follow the numbers? We know that work is force times distance, but what do we measure force in? And what do we measure distance in? Bring in a bathroom scale to give them some hints, and a large heavy object like this rock. Put it on the scale. What we're doing here is measuring the force of attraction between this object and the earth, or the force of gravity. So we're measuring a force, and that force of attraction is equal to 6 pounds. So we have the units for force. What is actually happening here? Maybe we should take a little look at gravity. The earth is attracting this object, and the scale and the table are holding it up. They're pushing back against it. For the 6 pounds of force that the earth wants to pull on it, the scale and the table are pushing back up with an equal amount of force, 6 pounds, to keep it from moving. Think of this, if I held it out here in air and let go of it, where there was no equal force holding it up, it would of course fall, it would move, and the earth would do work on it. If I held my hand under it here and held it stationary, I would have to exert 6 pounds of force continuously against it, continuously against the force of gravity to keep it stationary. Now if I want to do some work on the object, I'm of course going to have to exert more than 6 pounds of force on it to get it to go this way. Let's say I exert 7 pounds of force. So I'm exerting 7 pounds of force now, and all of a sudden there's 1 extra pound pushing up that way, so it's going to move. And I exert that 7 pounds for the distance of 1 foot. I have now done 7 foot-pounds of work, and that's how we measure work, in the foot-pound. If I happen to move it 2 feet up, 1, 2 into the air, then I will have done 7 times 2 feet, or 14 foot-pounds. So this is how we measure the proper units of work. Plus we're starting to get an understanding of gravity. And if all this doesn't confuse you, there's one more term we can bring into the picture, and that's power. What is power? Think of 2 men, a strong man and a weak man, and they're both doing the same amount of work. The strong man, of course, will do the work in less time because he's more powerful. And that's what power is. It's the amount of work per time. How much work gets done in a certain amount of time. Horsepower. Everybody's heard the word, but how many people really know what a horsepower is? Good trivia question. A horsepower is 550 foot-pounds of work per second. That means that if you're exerting 1 horsepower, you're moving 550 pounds 1 foot per second. That's pretty powerful. If you're measuring electrical forces, the unit of power is the watt. Now let's go back and take a look at gravity. What is this elusive force we call gravity? Well, to understand gravity, it's important that we first understand the difference between the 2 words, weight and mass. Mass is the amount of material in an object, how much stuff is in here, and it's independent of where it is, which means that if I take this rock far out in space, away from all other massive objects, it's still going to have the same amount of material. Weight, on the other hand, is a force of attraction between one particular mass and another particular mass. And if we're on the surface of the Earth, we're talking about the force of attraction of all masses toward the Earth, and it always pulls toward the center of the Earth. To measure this force of attraction, all we have to do is put a spring balance in between the rock and the Earth, and it'll push down on the spring. This particular rock has a force, or a weight, of 6 pounds. If I take this rock to the moon, the force of attraction to the moon is much less, 1/6 as much. So the weight on the moon will only be 1 pound. And for you people out there that are trying to lose weight, what you really want to lose is mass. Because if you went to the moon, you'd only weigh 1/6 as much and you'd lose lots of weight, but you'd still look the same. So you want to lose mass. Now let's take a look at gravity. Gravity is a force of attraction between all masses, and it's dependent on a couple of things. First, it's dependent on the amount of mass in the two objects that are attracted together. And secondly, it's dependent on the distance that separates these two objects. Let's take, for example, this ball and me. Both of us have mass, and there is a force of gravity that attracts this ball to me. But because our masses are so very small, that force is not great enough to make this ball go like that and stick. On the other hand, if you take the attraction between this ball and the Earth, the mass of the Earth is so very great, we now have a measurable force. And if I let go of this ball, it doesn't just hang in the air. It gets sucked toward the Earth. It's attracted toward the Earth. The force of gravity is pulling on it. The second factor, the distance that separates the two objects, is also very important. If I take this ball higher into the sky, the force of gravity acting on it will be reduced. This means that this ball will not weigh as much up at altitude than it does on the surface of the Earth. And as we go further and further out into space, the weight becomes less. And you're probably all saying, wait a minute, I thought things were weightless out in space. That's another question. The force of gravity is always acting on this object. And if you don't really believe that, think of this. How come the gravitational attraction of the moon can reach out through 250,000 miles of space and pull the water on the Earth, bulge it up? That's the attraction of the moon pulling on our Earth. And it's the attraction of the sun that keeps the Earth in orbit. But let's go on. Let's think of some more interesting things. If I take this ball further into space, there is a point somewhere between the moon and the Earth. It's closer to the moon, and the force of attraction of the moon pulling on the ball is equal to the force of the attraction of the Earth pulling on it, and really at that point in space this ball is truly weightless. And another interesting idea. What if we started digging a hole into the Earth and started going down deeper and deeper? As we go deeper, we start to find more mass of the Earth over our head, and that mass is now pulling upward on us. And the rest of the mass of the Earth is, of course, pulling downward on us. So we'd start to lose weight, less force as we go deeper, and eventually somewhere in the interior of the Earth, near the center somewhere, the force of the Earth would be equally pulling outward on us in all directions, and once again we would be weightless. Now let's deal with this question of how these astronauts appear to be weightless as they're circling the Earth. Imagine yourself standing on a mountaintop. You have this ball and you're going to throw it as hard as you can away from you. As you throw it, the ball goes outward a certain distance, and the force of gravity of the Earth draws it toward the Earth, and eventually it hits the Earth at a certain point. Let's say now that you pick up a rifle and you fire it. The velocity of the bullet is so much greater than the ball you threw, it will go much further out, but it will still be drawn down and hit the surface of the Earth. I hope you can see what I'm getting to, because now we're going to take the ultimate Chinese firework and we're going to fire it. The velocity is so great that as it falls, the Earth curves away underneath it, and the firework continues to fly around the whole Earth and come back around to us. We've now achieved orbit. And orbital velocity is the speed you need to achieve to get something to orbit the Earth. What it is doing is constantly falling, and these astronauts that are circling the Earth are constantly falling toward the Earth. Their forward speed is so great that they don't hit the Earth. And here's a good thought question for your students to reinforce this idea. All you need is a roll of masking tape and a large marble. Put the marble inside the masking tape and spin it around. As it spins, ask your students what they think will happen when you lift the tape up. Will the marble continue to spin around in circles? It would suggest it looks like it would, but in fact it goes flying off in a straight line somewhere. As the marble's spinning around in the circle, we're constantly exerting a force, bending its motion, pulling it back inward each time, and it's the wall of the tape that's doing this. If you lift the wall up, that force is no longer there, and the marble goes off in a straight line. This is what would happen to our spacemen who were orbiting the Earth if all of a sudden the force of gravity disappeared. We're starting to develop an idea now. That idea is that an object has a tendency to continue moving and in a straight line as long as there's no other forces acting on it. In this case, though, we have the force of gravity that's constantly changing the direction of the spacecraft. We could also have air resistance if the spacecraft isn't high enough. That would slow it down and bring it back to Earth. Then, of course, we have the rocket engines, which can either speed it up or slow it down. These ideas and some demonstrations and activities to follow will serve as an introduction to some basic yet very important laws of motion. There's a tendency for all stationary objects to resist motion. An example of this is a car that needs to be pushed for a push start, and there's only one person. Think of the possible ways you could do this. One way is to get behind it and push it like you normally would, but a second idea is to get back about a half a block and get a giant log and charge the car and hit it with as much force as you can. Wouldn't the greater force make the car go faster? Well, I hope you don't try that, because that car has what we call inertia, the tendency to resist a change in motion. And you know as well as I that you'll do some damage on the car. We can illustrate this tendency to resist motion in some simple demonstrations. First, you can get a playing card and a coin and a cup or a glass. And if you push the card slowly, like you're pushing the car, you see that the quarter moves. But if you flick the card, you see that the quarter falls directly into the glass. The quarter has this inertia, this tendency to resist motion. It can be demonstrated further with a stack of checkers. I've got 4 checkers stacked up, and I'm going to hit the bottom checker with one lone checker. Watch what happens. The bottom checker experienced a very large force over a very brief period of time, and the top checkers remain stationary because of inertia. One more demonstration we can do, and it's a rendition of the tablecloth under the 7-course meal. This one, you just need the top to a pen and a piece of paper. Hang the piece of paper over the edge of a table and carefully balance the pen top on top of the paper. Challenge your students. How would you get this paper out from under this pen top without the pen top falling over? Well, the secret is use this idea of inertia. Wet your finger and snap the paper. And if you do it just right, the pen top stays right there. This law of inertia was investigated and explained by Sir Isaac Newton in the 1700s. Incidentally, it's called Newton's first law. He went on in this law to explain moving objects, and he found that an object in motion has a tendency to stay in motion and continue in a straight line. We see the effects of this every day when we drive in a car. When the car stops quickly, we're thrown forward. This is because we want to continue in motion. When the car goes around a sharp turn, we feel like there's an invisible force pushing us outward. What is really happening, the force is acting on the wheels of the car, pulling the car inward, and we just have that natural tendency to continue in a straight line. Incidentally, this is an important reason for wearing seat belts. You can demonstrate this with a model of a car and a person. Put the person in the car, move the car along a table, and then stop it quickly. Watch what happens to the person. The person goes flying forward. You can also get a bucket of water and swing it around your head, and because the water has a tendency to go in a straight line, it stays in the bucket. And that really works. And you can identify an egg, whether it's raw or hard-boiled, by spinning it. Once you get it spinning pretty quickly, you can put your finger on it and stop it and then let go of it, and it'll continue to spin. This is because the liquid is still moving inside the shell. Sir Isaac Newton continued to study motion, and he formulated two more laws. His second law states that a heavy object takes more force to accelerate it than a light object. For example, to get a small car to go from 0 miles an hour to 20 miles an hour wouldn't require as much force as it would to get a large truck to do the same thing. His third law is that famous law, for every action there's an equal and opposite reaction, and explains how all of our rocket engines work. In fact, every force, there's always an equal force working in the opposite direction. You can demonstrate this one with a balloon. You blow the balloon up and release the air out of it. When the air, which has mass, goes that way with a certain amount of force, the balloon will go in the opposite direction with an equal force, and you'll see what happens. Let's do an experiment now that includes many of these principles of mechanics. Once again, we're using our inclined plane, and along with it, two marbles of unequal size, the bottom of a milk carton, and a ruler. The first principle to cover is the idea that energy is stored in an object when it's taken upward. This energy is called potential energy, or stored energy. When we let go of this marble, it begins to move. The potential energy is now being converted to what we call kinetic energy, or energy of motion. Now the experiment, what we want to find out is which marble has more energy, the large one or the small one. First, which marble would take more work to get it up to this particular height? Well, we can make a guess from that. The next thing we want to do is set up our milk carton at the end of the ramp, launch the marble by just letting go of it and letting it hit the milk carton. When it hits the milk carton, it pushes it off a certain distance. Now it's important that the marble stays in the milk carton on every run. If it falls or rolls out of the milk carton, we don't count it as a run. Then we want to measure the distance, the closest point of the milk carton to the closest point of the ramp. And this one comes out to be 6 centimeters. You'll find that you have to repeat this about 10 times and maybe average, divide by 10 to get the average amount of movement of this milk carton. Then we want to go on and do the same experiment with the smaller marble. By doing this experiment, your students will find out that, as expected, the larger the mass, the more energy that's stored into it and the more energy that's put into the milk carton at the end. Much can be learned from this experiment. If your student groups keep the variables constant, they should come up with similar results. You should have them go on and change other variables, change the ramp height, or change the size of the milk carton, and see how that affects the results. A final topic in mechanics is understanding the definition of speed, or average speed. If we know the distance an object travels, which we can measure, and we know the time it takes to cover that distance, which we can also measure, we should be able to calculate the speed, or the average speed. It's simply the distance over the time. Let's say a car travels 110 miles in 3 hours. What is its average speed in miles per hour? Well, it'll be 110 divided by 3. Whether we're calculating the speed of a snail in centimeters per hour or the speed of a rocket ship in kilometers per second, we're calculating speed. And if you take an object and drop it off a high bridge or a cliff, and you count the number of seconds it takes before it hits the ground, you can find the distance by just remembering 16 TT. You take the time in seconds, multiply it by itself, and then multiply that number times 16, and that'll give you the height in feet. Rounding out this series in physical science are investigations into forms of energy. These include heat, light, sound, electricity, and magnetism, and they're on part 2 of this physical science series. To get science materials, contact the companies listed in the printed outline. They'll send your school a catalog.